Right? We're going to be now looking at compression systems, right? We're going to use grid shells as our kind of type to experiment with these types of systems, right? So here's an example of a grid shell that we've been doing some research on, and a grid shell, as opposed to in contrast to a tension system, is going to rely entirely on compression, right? So whereas all of the forces within the net were acting in tension internal to the surface of that shape, in a grid shell they're all going to be working in compression, right? Which means that where we had just an anchor before and an internal force, we now have to work with an external force, right? This is probably going to be coming from gravity, right? Where the grid shell has to resist gravity by allowing a compression force to move through the section of the grid shell, right? So there are both ring and meridian or meridian forces that pass through the surface of a grid shell. In the case of what we had as an example for the tension system, those were also similar. Those would also be the same terms for the forces that are traveling in the different directions. But whereas the tension system also had opposite curvature in the two directions that composed that surface, the grid shell, the curvature is going to be consistent, right? They'll both be curving in the same direction no matter which way you're traveling through the surface, right? And a grid shell really gets all of its strength from its double curvature. Okay, so some examples of a grid shell. Again, looking back at Frey Otto, his multi-hull Mannheim, which is a simple grid. Well, not exactly a simple grid, but it is a relatively simple grid, but it has a free-form boundary that constrains that grid, right? Some interior shots of that, right? So it's able to span quite a bit of space. And the basic premise for any grid shell, just like what we're going to be doing here in a second in Kangaroo, is that if you have a two-dimensional grid, if you push the edges in, right, it's going to spring into a grid shell shape. Right, again, some examples interior to the multi-hull. All right, so let's go ahead and bounce back over to Kangaroo. I'll save this file and close it. And just to give you a sense of where we're going, we'll open up the grid shells file. So this should look pretty familiar. It's almost the exact same thing, except for we're going to use a different, or at least another force here, and add it to the physics engine. And then while we're here, we'll go ahead and add some visualization cues afterwards. Instead of just visualizing our standard red mesh that comes from the results of the physics engine, we'll go ahead and add a little bit of color to it. Okay, so I'm going to get rid of all this geometry that we just sketched in the Rhino environment and go ahead and close this file, but open up the file we were just working on, because we're actually going to build from here. Building up from the nets, we're going to go into grid shells. Right? So I'm going to save this as my grid shells file, the working version. Okay, and let's go ahead and make our mesh again. From primitive, this time let's just use a plane. To make sure you specify that you want it to be 1 by 1. And I missed that again. 1. All right, so we have a single mesh face again. And let's go ahead and input this at the top as our input mesh. Okay, so if we were to turn the preview on of our quad divide, we're back to seeing our divided mesh with a bunch of internal segments that are going to become springs. All right, so let's talk a little bit about what we're going to do with our grid shell. The first thing that we're going to look at is that we need to apply a force, right? So an external force to make this act in a grid shell is going to come from gravity, right? So we need to apply a single force to each one of these vertices so that they as particles have an additional force applied to them. So if we go to the kangaroo forces tab, we're going to grab the unary force, right? This is a vector force acting on a point. Gravity is just that, a vector force. It goes down. So let's go ahead and grab this object and drop it into the canvas. We zoom in. It asks for the point to apply the force to, and the force that is described by a vector, right? So what are the points that we're going to apply our force to? Well, we're going to apply it to the vertices of our decomposed mesh. So each one of these vertices here will get a force applied to it. So in order to do that, we need to then supply the force, which is going to come from a vector. So let's go to our vector tab. Under vector subtab, let's grab the unit z, right? Gravity always operates vertically, so we'll choose the unit z, connect that up to force, and then we need to specify a factor, right? So let's go ahead and use our standard factor for gravity, which is 9.8. I'm going to do that by specifying a panel. Double click, 9.8. This is my gravity factor. Connect that in. All right, so now after the vector and points have been supplied to this object, it says that we've now created a kangaroo KU force, kangaroo unary force. All right, so now what we want to do is we need to start, because we're applying more than just one type of physical object to the simulation, we're using more than one, we want to take all of our force objects, our physical objects, and bring them together into one stream so that we can supply them to the physics engine. So in order to merge our streams, our wires, we're going to go to Sets, Tree, Merge. We're going to merge a bunch of data streams. So the springs from mesh and the unary force are going to come here. I'm going to zoom in so I can get rid of this extra input, and then group it, and this is going to be all physical objects, right? So forces, springs, etc. Right? And then we can take, you can see here that the kangaroo engine calls them force objects. So we'll take all of them and drop them into the force objects input. Right? If we hit true to reset, our physics engine is happy again, it's not red. All right, so we've got our physical objects all brought together. We have the unary force and the springs working, or at least we think we do because we haven't run the simulation quite yet. The next step is we want to find maybe a little bit more dynamic way, a more dynamic way to find all the vertices that are here at the corners, right? And just let them be pulled from the mesh without having to actually specify them in Grasshopper. So if we go over to the Kangaroo tab, under Utility, there's another nice object here that allows us to get the mesh corners from the boundary, right? This is based on a threshold. So let's go ahead and drop this object into the canvas. This asks for the mesh for edge extraction, the angle tolerance for the difference between the adjacent edges. So if we go ahead and drop the quad divide into here, we'll see that coming out of the this object, we have the 4 corner points already, right? So we don't actually have to supply them in Grasshopper from Rhino. So that's a little bit a way to make it a little bit more dynamic for the user. All right, and this supplies us the 4 points that are found in this case. All right, so the same way that we had all of our physical objects, let's go ahead and copy and paste this grouped merge and bring the result of this into the mesh corners into this object. Get rid of D2, and instead of all physical objects, this is going to become all anchors. All right, so those are all the anchors, and they can go into the anchor points input. And then we have our geometry coming from decompose. And maybe slide some of this around a little bit, clean it up. I'm going to go ahead and right-click on this and say that the wire display should be faint so I can see clearly what's going on. All right, this all looks good. All right, so I'm going to save, and now it's time to test our simulation. We can go ahead and delete this extra floating object over here. All right, so let's reset the simulation and then release the timer. If we enable the simulated mesh, we'll see actually something very similar to what we saw before. Now, the rest length multiplier from the last exercise was below 1. And if we want to go to a grid shell, we want this to be 1 or so, maybe a little bit below or a little bit above, but around 1. Right? We don't want to go too far because it actually starts to find all kinds of overlaps and such. It gets kinked, the springs do. So if we're about 1, now instead of being in a completely tensioned system, right, we have a grid shell. Our curvature is convex. If you're looking at it from the inside, convex in both directions, right, as you move through the grid shell. And it's very much influenced by the pressure of the gravity force. All right. So this file seems to work, right? Let's add in the, in terms of the basics of the simulation, let's add in the visualization trick that we were talking about before to make it look a little bit nicer, give us a little more information in our viewport. And then we'll look at some alternative ways to use this as a kind of sketching tool to develop some different forms that are based on grid shells. All right, so whenever I'm doing anything, much of anything in my Grasshopper file and I'm working with a simulation, I want to make sure that I block my timers so that it's not trying to calculate over and over again in the background. All right, what we're going to do is we're going to go to the geometry out area of the file after the physics engine, and we're going to start to develop a little bit of a logic to color this shape based on a certain kind of analysis, right? So at first, let's go ahead and just take each vertex and let's give it a color based on how high it is in the z direction. So if it's higher, it's going to get one color. If it's lower, it's going to get another. All right. So again, coming out of geometry, we have a list of points. All right. So these points, we can take them apart to get their z positions by going to the vector point decompose object. So we'll take the geometry out and decompose it. So now each one of these points has a corresponding z value, right? Take that z value and under the math domain tab, we want to find what the extents of all the z values are in the list. So we'll take the bounds of z. This gives us a domain, so between 0 and 55 units. And then we're going to use that domain and the z value to get a specific color from a gradient. That's under params input. So if I right-click presets, we'll choose one like this. All right. I'll move the grips off to get rid of these. I think I want blue to be on bottom and red on top, something like that. All right. So the gradient asks for the value that describes the lower limit of the gradient, the upper, and then the value to test. All right. So the z is our value to test. Now we just need to take the domain and break it into its minimum and maximum. So that's under math domain components. So that gives us the start and end isolated so that we can connect those to L0 and L1. That gives us a list of colors coming out, and we can use that to color each vertex, right? This analysis is happening per vertex, so we can use this list of colors to color each vertex. right? So now our mesh is being previewed with a specific analytical relationship established. So if I reset and then let my simulation run again, you'll see that as it simulates, it updates so that all of the high areas are red and the low areas are blue.